Let's draw some structures. We have two very similar questions here. Each one talks about sodium and chlorine, but the first one says uncharged atoms, and the second one says ions. So there's very important words you have to look for every time. Sodium and chlorine. Sodium is Na, chlorine is Cl. So I'm just going to write that for each one here. For uncharged atoms, we go right to our reference table and see what it says about the number of valence electrons. For sodium, it says we have 1 valence electron, so I'm just going to draw that right up top for each one here. And for chlorine, it says we should have 7 valence electrons. So the first two always go up top, and then clockwise around, not giving 2 to either side until everyone gets 1. So there's my 7 electrons for chlorine and 1 for sodium. And the same thing on the bottom here. Just fill them in. 1, 2, 3, 4, 5, 6, 7. Okay, now sodium we're done, and chlorine up top we're done because uncharged atoms are directly what the reference table says. For ions at the bottom, something has changed. So for sodium, we have to look it up and see that sodium forms a +1 ion. Well, how are we going to get to be a +1 ion? That happens by losing the 1 electron sodium has. So I'm going to cross that off right here, put brackets around it to show that it changed and that I didn't just forget to draw that electron, and write a plus outside. For chlorine, it says a couple of different options. We care about the -1. So how do we get to be a -1 ion for chlorine? We do that by gaining 1 extra electron in the 1 empty spot that chlorine had there. I put brackets around it to show again that something changed. I didn't just draw the wrong number of electrons. And again, put a minus sign out there for chlorine to show that it has a charge. What do these two things do now? Why do we end up drawing these ions? That's so we can do what the lesson says up top, and that's form ionic bonds between the positive and negative ions. We'll look at 3 types of bonding in this chapter, and realistically it's more like 2.5 types of bonds. These are ionic, covalent, and metallic. You can tell the difference between them based on the types of elements that are involved in the bonding and what's going on with the electrons, and we'll see each of them in turn. As you can guess from what we've done already in the title of this video, we're talking about ionic bonds. These ionic bonds will form from charged ions, and for ions to attract each other, they need to have opposite charges. That means they'll usually be bonding between a metal and a nonmetal, but it could also be between one of these elements and a polyatomic ion with the opposite charge. So that means either a positive metal ion with a negative polyatomic ion, or a negative nonmetal ion with a positive polyatomic ion. But anytime you see a metal in a compound, we're looking at some kind of ionic bond. Ions only form because atoms have different attractions for electrons, or electronegativities. And you see this here on the 0 to 4 scale. So 0 is a really weak attraction for electrons, 4 is the strongest attraction for electrons. Metals have low attraction for electrons, or low electronegativity, and easily lose their electrons to form positive ions. While nonmetals, we see having a high electronegativity, a high attraction for electrons, which helps them pick up extra electrons to form negative ions. These are not separate events though. A nonmetal actually takes the electrons right away from a metal that it's going to bond with, producing a negative nonmetal ion and a positive metal ion. Those positive and negative ions now can actually attract and form an ionic bond. This gives us the definition of ionic bonding, which is that ionic bonding involves the transfer of at least 1 electron from one element to another, or between polyatomic ions. And this word here, transfer, is the word to look for. Anytime you see this word transfer, you need to think ionic bonding. In your minds, transfer needs to make you think ionic and vice versa. We know that opposites attract, so once the electrons are transferred, moved from one element to another, the oppositely charged ions that form will attract each other like magnets to form an ionic bond. A few things to look for in identifying ionic bonds. What types of elements do we actually have? If it's a metal and a nonmetal, or either of them with a polyatomic, then it's ionic bonding. Anything with a metal is ionic. Remember, 2 metals can't go together. So if you see a metal, it's got to either be a metal and nonmetal, or a metal with a polyatomic, and either of those would be examples of ionic bonding. Compounds like salts and electrolytes, words you probably hear a lot but don't really know what necessarily they mean, we'll learn about them in forthcoming chapters, and they're going to count as ionic compounds also. If we compare the electronegativity values of the elements involved, there'll be a difference larger than 1.7. So remember that electronegativity is the pull on electrons, how strong something wants electrons. Metals really don't want electrons, they have low electronegativities, and nonmetals do want electrons, they have high electronegativities. So if you have one of each attracting each other, one of them will have a small number, one will have a larger number. The difference in these two values would be at least 1.7, showing there's a big difference. Because one element is attracting electrons more than the other element, the bond will be kind of lopsided or unbalanced. The electrons in that bond will be kind of leaning towards or crowding to one side as opposed to the other. And we refer to this as a polar bond. Just like a globe has poles with one distinct end and another distinct end, our bodies have heads and feet, 2 distinct ends. If you remember this term from bio, polar just means there are 2 distinct sides. And in this case, it's going to be two different elements on either side of the bond. So the bond has very distinct ends. It's very clear to see one element on one side and a different element on the other side. That's why we call it a polar bond. In a few chapters, we'll talk a little more about these processes of losing and gaining electrons. So I'm going to tell you the words we'll use then as a sneak peek. Losing electrons is called oxidation, and gaining electrons is called reduction. In any case, the metal sodium in this example would lose its electron, and it doesn't just disappear. It's transferred to the nonmetal chlorine. Anybody see a place on the chlorine where that one electron fit pretty nicely? How about this empty space right there? Does it seem like it would work? Say abracadabra, and our electron jumps from the metal sodium, pulled by the stronger electronegativity of the nonmetal chlorine. We saw previously that once we move electrons around and make ions, we need to draw brackets around a symbol to show that we didn't just draw the wrong amount of electrons. So put brackets around each ion and write the charges outside. Sodium is a +1 charge, so I do brackets with a plus sign. You don't have to actually write the number 1. And chlorine makes a -1 charge, so do brackets with a minus sign. Again, you don't have to write the -1 number. These oppositely charged ions attract, so I need to write the whole thing a little bit closer together. I'm just going to put them physically next to each other on the page to show the attraction. And just always remember that any ion gets a bracket written with charges outside. That shows it's different from a neutral atom, and we didn't just make a mistake and forget to draw the electron dots or put too many electron dots. To review, for ionic bonding between differently charged ions, you need to draw the symbols near each other. Ions go in brackets with the charges written to the top right, and always look at the charge of each ion and count how many electrons it should have. Don't assume anything. But the metal usually has no valence electrons, no dots, and the non-metal has all 8 valence electrons, 8 dots, 2 on each side of the symbol. Then just put them next to each other to show that they're being attracted. As we start to do Lewis structures for ionic compounds now and not just individual elements, we have to look for a couple of bits of information. One is what type of ion, what charge of ion each element actually forms, which we've been doing already. We go to the reference table and find that. But also we have to pay attention to how many of each element there are. So in the first example here, I have one Li and one F. I need to draw the correct number of these things, and then we just have to actually put them together. So as we've seen before, for Li and F, we would start out by seeing what those elements' ions actually look like. For Li, we go to our reference table and it tells us that it's an Li +1 ion. So it usually has 1 electron, but it lost that to make the +1 ion like this. And F usually has 1, 2, 3, 4, 5, 6, 7 electron dots. But to make the -1 ion, it would have gained an extra 8th electron right there. So it would get brackets and a minus charge, just as Li gets brackets and a plus charge. That's still just really 2 different ions though. So we want to put them together to show that they are actually a compound. So it's going to redraw it over here, Li with its brackets and plus charge, and right next to it, F with its 1, 2, 3, 4, 5, 6, 7, 8 electrons, brackets, and a minus charge. Now we can see that they're close, they're attracted to each other. That's going to be our ionic compound, Li and F. For the next one, MgO, same kind of thing. We would look up and see that Mg makes a +2 charge, and O will make a -2 charge. So I'm going to draw Mg. Normally Mg has 2 valence electrons, but to get that +2 charge, we have to get rid of those both electrons and put in brackets with a +2 charge written to show that something has changed. And right next to it now, to show that they are attracted, I'm going to do the oxygen. Oxygen normally has 1, 2, 3, 4, 5, 6 valence electrons, but this -2 charge up here tells me, that should be an arrow, it looks terrible, but should be an arrow, shows me that we gained 2 extra electrons, so I'm going to put them right in the empty spots here for 7 and 8, and I'm going to put brackets around oxygen and write its -2 charge to show that it is an ion. The subscripts or lack thereof in this formula up here, there are no numbers, so we know we only have one of each one, says that Mg with a +2 charge, O with a -2 charge, that's what our ionic compound looks like right there. The third example at the bottom now, we finally get a subscript. So now we have to worry about drawing a magnesium with 2 fluorines. We have to make sure we draw the correct number of these things. So again, Mg we just saw right there makes a +2 charge. I'm just going to go ahead and draw the exact thing we did in the second example. Mg in brackets, it lost both of its electrons to get a +2 charge. But I'm going to draw fluorine now, and it says that I need 2 of the fluorine, so I just have to make sure I draw the correct number of these things. So I'm going to draw 1 fluorine over on this side and 1 fluorine on this side to spread out a little bit. Now, fluorine normally, according to a reference table, has 7 electrons in its valence shell, so I'll do 1, 2, 3, 4, 5, 6, 7 for this fluorine, and 1, 2, 3, 4, 5, 6, 7 for that fluorine. That's not normal though. We usually would have that kind of situation, but we know magnesium lost 2 of its valence electrons. Where'd those valence electrons go? Well, 1 valence electron went over to this fluorine on the right to help it fill in its valence shell, so it now has 8. So I fill that 8th electron in right there, give this fluorine a bracket with a -1 charge, and the second electron that was lost by magnesium goes to the other fluorine, so I'm going to put that over here. It goes over there. Its valence shell is now filled in, so fluorine also gets brackets and a -1 charge. I've now got 2 -1 ions of fluorine with a complete outer valence shell each, and I have the 1 magnesium +2 ion with its valence shell underneath. We don't have to draw that because we only care about what was on the outside, which is now empty, and it gets a +2 charge and its brackets. Normally with this kind of thing, you'll see questions like the last slide where you're told exactly what the formula looks like and you just have to draw the thing. Sometimes though, you'll see a question like this where it says make a bond between S and Y. It doesn't tell you what that molecule looks like or anything else about it. And we just have to go look up the charges on the periodic table. Then we can do a crisscross to see what our molecule looks like, just as we've done in previous chapters. So I'm going to go do that. I'll look this up. Between Y and S, Y is actually the metal, so even though it's written second in this question, I'll write on the left because remember metals always go first. So Y and S up here. Y, when we look it up, it has a +3 charge when it forms an ion, and S forms a -2 charge as an ion. So I'll do a quick crisscross, and I'm going to drop the 2 from S down to show that I need 2 of the Y's, and I'll drop the 3 from Y down to show that I need 3 of my S's. Now I know this is what my molecule has to look like. I'm going to have to draw out 2 Y ions and 3 S ions. I haven't drawn something this big yet, but it's the same exact process we've been doing, so nothing different. I'm going to change colors just to kind of separate this step from the last one we did, and let's do this. I'm going to draw my 3 S's first. I'll just draw this over here. S right here, another S, and another S. I give myself plenty of space. Now I'm going to have to draw electron dots and brackets, and I'll draw the Y's just kind of underneath them. Space out a little bit again. So Y, let's do that first, get that out of the way. The metal, it says Y usually has 2 valence electrons, so each of these guys down here would have 2 valence electrons, except we know up here that's a +3 charge. That means we had to lose 3 electrons. So I'm going to go actually right ahead and delete those 2 electrons I just drew for each one, because those will be lost. That's how I get to be a +3 ion. Now, those are only 2 electrons lost. The third one is just one of the under electrons that we never draw anyway, so we don't have to worry about that. We're just going to leave this as is. We just get rid of those 2 valence electrons. We now put each of these things in brackets and write +3 to show that each of them is a +3 ion. For the S's now, it says S on the reference table normally has 6 valence electrons, so 1, 2, 3, 4, 5, 6 for him, 1, 2, 3, 4, 5, 6 for him, and 1, 2, 3, 4, 5, 6 for him. It does tell us though now that it's a -2 charge on the S ion, so each of these ones has to get 2 extra electrons. So I'm going to do 1, 2 right here, fill him in. He's now got 8, and I can put him in brackets and write -2 for his charge. This guy in the middle gets 1 and 2. He's now got a complete 8. He gets brackets and write a -2 charge. And this one all the way on the right gets 1, 2 extra electrons. He's also now got a complete set of 8, and he gets brackets with a -2 charge. So we didn't have what our molecule should look like originally. We can use the charges written in the reference table from these elements to now get to this point here where we know what our molecule should look like, and then we just have to actually go ahead and draw it as we've done before. We've got 3 S's, each with a -2 charge, each with a complete set of 8 valence electrons, and we have 2 Y's, the yttrium metal. We took their valence electrons away, so each gets brackets and a +3 charge. -2, -4, -6 charge total up here, +2, +6 charge on the bottom, balance each other out. The whole thing balances and cancels, and that's our ionic compound for Y2S3. Same thing as last slide. Look up the charges and do a crisscross to see how many of each element are in the compound, then draw the correct amount with the right number of electron dots, use brackets, and write charges. Pause the video here to work on these, and I'll write out the answers. These are both good videos that we'll probably watch in class at some point, but I'll also post the links in OneNote either under this video or in their own page in case you want to check them out on your own. To end this part of the chapter, let's take a look at properties of ionic compounds. I suggest always thinking of salt. Just picture a chunk of salt as a crystal and use that as a model of compounds held together by ionic bonds. Ionic substances are hard. So again, think of a salt crystal. It's hard. It's maybe something you can crumble pretty easily, but it is a hard substance. They also have high melting and boiling points, so you need to get them very hot to cause a phase change. They do not conduct electricity very well as solids, but they do conduct electricity well as liquids or when dissolved in water. So if you send electricity into a salt crystal, it's not going to do anything. But dissolve that salt in water and it works very well. If you hear the term electrolyte on a Gatorade commercial, it's saying that the sports drink puts charged ionic particles back into our bodies, which are lost during exercise, which is why sweat tastes salty. We need to conduct electrical charges in our nerves and muscles in order for our bodies to work properly, and Gatorade or things like it will put these back into our bodies to help us out. Hopefully you think this is a little bit funny, at least to appreciate the pun. If not, you might want to go back and rewatch the video. You know the deal by now. Go complete the form, pick this up tomorrow, we'll have a test in a couple days.